here today. Looks like Ian started the recording. Great, and she's going to be speaking to us today about gaps between zeros of the Riemann zeta function.
Great, thank you, Larry, for the introduction, and thanks so much for the invitation. Of course, it would be nice to be there in person, but this has made it easier. I just got done teaching a class, and now I'm giving a seminar at Vanderbilt, so it kind of makes things go a little bit faster. So what I'm going to do today is that this problem has fascinated me for a long time. It has a really rich history. It has its fingers in a lot of different cool problems from number theory. And so what I've tried to do is there are many parts of the talk where you can kind of re-enter the conversation. And I also want to make sure that, if there's anything that is just really not making any sense, the whole point, hopefully you'll walk away from this and say, that's a cool problem. So if anything doesn't make sense, I've got the chat open, you can ask a question, you can unmute yourself, it can be really informal. But hopefully you'll walk away with an understanding of why I think this is a cool problem. Okay, so all right, so to get started, we have to remind ourselves about the Riemann zeta function. So we have the Dirichlet series, we have the Euler product. The zeta function has meromorphic continuation to the complex plane. Just one pole, simple pole with residue 1 at s is equal to 1. Now, if you know the so-called trivial zeros, these come from if you know the functional equation. So as soon as you know the functional equation, that tells you how to move from the right of 1, or so let's say it this way. There's a functional equation that relates zeta of s to zeta of 1 minus s. And so through the functional equation, you can find that there are zeros of the zeta function at the negative even integers. So we call these trivial because as soon as you know a little bit more about the zeta function, you can find them, no problem. And then there are the mysterious non-trivial zeros that we're interested in that are in the so-called critical strip, right? So if here is 1, then the Dirichlet series and the Euler product converge, and so we kind of know what's going on over here. The functional equation lets us hop over to the left of 0. We have trivial zeros at the negative even integers. We have one problematic place at s is equal to 1, that's the pole. And then we're interested in the so-called the trivial zero, the non-trivial zeros that are in the critical strip. And because of properties of the zeta function, because of the functional equation and the fact that the zeros are symmetric about the x-axis, once you get 1 0, you actually get 3 more, right? Because of symmetry properties. And when you dig into the proof of the prime number theorem, the better error term you can get is when the zeros are as far away from the 1 line as possible. And so because of this symmetry, that will occur if the zeros line up on the half line. So what we're interested in, whether we're assuming the Riemann hypothesis or not, we want to say, what can we say about the vertical distribution of the zeros of the zeta function? So the Riemann hypothesis is telling me where horizontally does it lie in the critical strip, and I'm going to be interested in the vertical spacing. Okay, so we can actually say quite a bit without too much work, just using classical results. So if you want to count the zeros of the zeta function, we might as well just look in the upper half plane because we have this symmetry. And so let's say we want to count the number of zeros of the zeta function in a box up to height t. All right, so this is not assuming the Riemann hypothesis. We have the surprisingly strong Riemann von Mangold formula that tells you how many zeros there are in this box that I've drawn when t is large. And so notice we have really the thing to notice is this t log t term. We've got some lower order terms, a term of size t, constant, something that's of size 1 over t. And then there's this extra bit here, s of t. This is the argument of the zeta on the half line. We're actually going to return to this later in the talk. It's going to be really helpful for understanding some of this distribution. But for now, just know that it's small enough so that we can say, well, if I can count how many zeros there are in this box, and the main order term here is like t log t, then this tells me the average gap between two consecutive zeros, right? So I just divide by the number of zeros, and I get like 2 pi over log of gamma n. And just to note that if you look up even higher, and maybe the zeros are between, say, t and 2t, if you look up in that area, then it's totally fine to replace this here with just a capital T. And we'll use that later as well. All right, so we have the average gap between the ordinates of the zeros of the zeta function. And so now let's consider the sequence of these ordinates. Okay, so we've got gamma 1. We know this is a little bit over 14, then the next zero. And I want to point out a subtlety here. I am not assuming that the zeros are simple. Of course, we think they are, but that we don't know that for sure. And it's actually a harder problem to approach this by assuming all the zeros are simple. There are actually no results in the literature so far where we've assumed simplicity of the zeros. And the reason why that's interesting is because when you want to talk about how small a gap can be, if we take the consecutive difference and divide out by the average spacing, you could say, well, if I have lots of multiple zeros, this could be zero infinitely often. And so it actually turns out, so I know that there's a paper in the works that's actually going to get some results where you've assumed that small results aren't happening because of hypothetical multiple zeros. We don't think that they are there, but nonetheless, that is an extra layer of the puzzle. Okay, so here's the question of the day. You take your difference, you normalize by the average spacing, and then you say, well, what can we say about the log𝛾𝑛 of this sequence? That will tell me about small gaps. Okay, sorry, the college just came by to mow the grass at my faculty housing. So sorry for that, it'll be loud for just a bit. And what can we say about large gaps, right? So if we look at the lim soup, what can we say about how big this normalized spacing can get? That's what we're interested in. Well, let's just think about what we have by definition. So by definition, the way we've set this up, mu is at most 1 and lambda is at least 1. But actually, we can make these inequalities strict because of some observations by Selberg and Fuji. So Selberg made this observation in the 40s and then Fuji again in the 70s, that there really does exist infinitely many zeros that are smaller than the average spacing and further apart than the average spacing. If you want to see a proof of this result, then you should get out your copy of Titchmarsh and go to chapter 9. There in the notes, Heath Brown gives a sketch for how you might actually prove this. It was not written down by Selberg or Fuji. All right, so by these kind of observations by Selberg and Fuji, we at least know that mu is strictly less than 1 and lambda is strictly greater than 1. However, we conjecture much more to be true. All right, so we conjecture that mu is 0, which means there are infinitely many pairs of zeros that are arbitrarily close relative to the average spacing. And we also conjecture that lambda is infinity, which means there should be infinitely many pairs of zeros that are arbitrarily far apart relative to the average spacing. So this is kind of what we get for free. This is one of our first observations, and this is the goal. And so before I kind of tell you about progress, where we are here, the first thing you might be wondering is, well, why do we believe that this is the case? All right, well, everything comes down to Montgomery's pair correlation conjecture. So if you haven't seen this before, let me kind of point out to you the pieces here that are the most important in terms of me convincing you about the conjecture that I just stated. So Montgomery's pair correlation conjecture here is telling you how to count how many pairs of zeros you have up to height t, whose difference is bounded above by some constant times 2 pi over log t. Now remember, if the gamma is like, if I replace this with a t and this with a 2t, this is what the t is going on here. So we're going to count pairs of zeros closer together where I can vary c, and then I'm going to divide out by the number of zeros total. And Montgomery conjectured that what I have here, I'm putting out in red, is the right way to approximate this, or here's an asymptotic. And so here's one thing to note. This integral is always positive and always strictly less than c. And so on the one hand, if you believe Montgomery's pair correlation conjecture, that means you can make c to be very, very, very small, which is going to force these pairs of zeros to be very, very close together. And you're still going to get something positive. And as soon as you get something positive, you found the pair that satisfies the product, satisfies the property. So on the one hand, we get the small gaps conjecture from believing Montgomery's pair correlation conjecture. Okay, well, what about large gaps? Where does that lambda equals infinity conjecture come from? Well, it also comes from Montgomery's pair correlation conjecture. So, okay, I haven't changed anything on the slide. This is the same conjecture. But now what you want to do is you want to look a little bit more closely to what's going on. So it's conjectured that this is the pair correlation function of zeros of the zeta function. And I would be remiss to not tell the story about why, like where this came from, where this conjecture came from. So the story is, in short, why you should never skip t. So Montgomery was at the Institute working on the pair correlation of the zeros of the zeta function, and he kept arriving at this pair correlation function. And at t, Dyson noted that eigenvalues from random Hermitian matrices have the same pair correlation function. So this connection has been supported by extensive numerical estimates by log𝛾𝑛, but it's still a conjectural connection. Now, in Montgomery's pair correlation paper, he also conjectures the higher level correlation of zeros of the zeta function, and also conjectures that they should also match the Gaussian unitary ensemble from random matrix theory. So if you believe Montgomery's pair correlation conjecture and the conjecture to random matrix theory, then on the random matrix theory side, the analogous problem would tell you that lambda is infinity. Right, so you can see Montgomery's 1973 paper. If you are interested in the higher level correlations, then one very nice paper to read is that of Rudnick and Sarnak on the higher level correlations of zeros of the zeta function. This is a couple of sentences in Montgomery's paper. Okay, so where are we if we have these conjectures? All right, now I'm interested in small gaps. If you have questions about large gaps, I'm happy to answer them. But here on one page, I've tried to put together the results we have on small gaps progress. And the thing to remember is we're trying to get mu is equal to 0. And if you notice these dotted lines, I've separated these results, and they're actually separated by method. All right, so each grouping is using a different method, and each method maybe assumes certain things or produces certain type qualities of answers. So the first approach by Montgomery, and then later gone through and made a little bit tighter by Goldstine, proved an upper bound on mu of 0.6072. Now remember, before we only had one, right, from Fuji and Selberg. So this is an improvement. It does assume the Riemann hypothesis, and it uses Montgomery's, what we know, towards the pair correlation to prove this result. And using similar approaches with this method, the result, I think where it stands right now with this method is 0.6039. Now in 85, Connery, Ghosh, Gonnick, Goldstine, and Heath Brown were at the Institute, and they used a different method that also assumes the Riemann hypothesis, but has a really nice property that the result doesn't just hold for infinitely many pairs of zeros, but for a positive proportion of zeros. So here you can see that the quality of these results are not as strong as what I listed above, but this result of it holding for lots and lots of zeros, not just infinitely many, is kind of the strength here. And now what's kind of a really funny story is that Montgomery has actually determined that the pair correlation argument does produce results for a positive proportion of zeros. And it's my understanding that he's writing this up. So that wasn't clear to begin with. And so now kind of these later results using a different method are actually already superseded in terms of quality because of this observation that's not trivial. Okay, so then the last section, you might say, whoa, we're in the 0.5s. Okay, this is better. I'm going to talk about this method. This is the method that's giving you numerically superior results. It also assumes the Riemann hypothesis, but you give up something. And what we're going to give up is that the result only holds for infinitely many zeros. I'm going to tell you kind of why you might want it to hold for more than just infinitely many. All right, so let's notice. So Montgomery in 81 developed this method with the log𝛾𝑛, and we're able to reduce the upper bound on mu to 0.5179. And then a couple of years later, Turnage-Butterbaugh gave a much more simplified version of Montgomery and log𝛾𝑛's method and won by a little bit. I'm going to tell you about, so there are two methods are equivalent, but the Turnage-Butterbaugh method is significantly simpler. And then later, Bowie, Milinovic, and Ng combined approaches from these previous two papers in an interesting way, and were able to make a significant reduction. So significant now is in the context of how these results are going. And then Feng and Wu made a refinement and changed the 5155 to a 515398. I think really in their paper, they just put a 4 here. But then Preobrajensky is really careful to note that this is what Feng and Wu really got, and he's able to get the result down a little bit more. Okay, so when you look at these results, I feel like there's some natural thoughts that people might be having. One might be, what's going on with the 0.5 stuff, okay? And you might also be wondering, like, why are people trying so hard and getting these small results? And so I can tell you from my own work that what goes into these methods is a lot of work and then kind of holding your breath and hoping you get the next world record. And so it's a lot of work that can actually pay off, not give you anything. And so what I want to do is I want to kind of tell you why people are working hard and where this 0.5 might be coming from. Okay, so now we're going to kind of start a story over, and we're going to start over and talk about the class number problem. All right, so new little story. So if we look at an imaginary quadratic extension, then what we're interested in is the size of the ideal class group. So just a quick refresher, this is the group of fractional ideals of K modded out by this subgroup of principal ideals. And the class number of K is just the size of this group, right? And so if you haven't thought about this in a long time, or maybe it's the first time you're seeing it, here's the reason why the class, one thing that kind of sells you on the class number. If the class number is 1, that means the size of your group is 1. It's just the identity. But if it's just the identity, that when you mod it out by the principal ideals, you got rid of everything. So that means your ring of integer is a principal ideal domain. But that's actually equivalent to being unique factorization domain. We get both directions because these rings of integers kind of have that property. They're Dedekind domains. Okay, so the class number being 1 tells you you have unique factorization, not too shabby. All right, so this goes back to Gauss. Gauss conjectured that the class number goes to infinity as D runs through negative discriminants. And this was actually proved by a collection of papers, Hecke, then Düring, then Mordell, then Heilbronn, each assuming a little bit, one paper assumes a Riemann hypothesis, one assumes a Riemann hypothesis is false. You put everything together and you can, with all of these pieces combined, you get the full conjecture. All right, so what this implies is that there are only finitely many imaginary quadratic fields with a fixed class number. And so then we want to classify them, right? So the class number problem is give a list of the fundamental discriminants for which the class number is fixed. All right, so when the class number is 1, meaning we have unique factorization, this was proved kind of in a different way by a collection of authors, Heegner, Stark, and Baker. And here's the list of the fundamental discriminants with class number 1. All right, and so the story is Heegner was a high school teacher and first proved this, and his work wasn't initially accepted. And so later, Stark and Baker around the same time proved this result, and then later Stark went back and proved that Heegner's approach was valid. So that's n is equal to 1, and so now you might say, well, what if n is greater than 2? And let's look at a simplified version of the class number formula when the discriminants are less than -4. So what do we have here? We have the class number, that's what we're after. Here's the discriminant. And then here is the L function, the quadratic L function at 1, where here we have a Kronecker symbol. What we want is a lower bound on the class number. We also have very good upper bounds on the class number so that you only have one window of places you have to check, right? We want to be able to classify these and kind of whittle down all of the cases. And so, the trivial lower bound is 1. All right, that's not so helpful. I mean, it's a group, so it's got something in it. And notice that this will also give you a lower bound on the L function. All right, well, what do you get if you assume the generalized Riemann hypothesis? Well, if you assume the generalized Riemann hypothesis, that means you don't have any exceptional zeros. And so we can get some bounds on the L function at 1. And then by the class number formula, that gives me an upper and lower bound on the class number. And so what you want is a stronger bound that's also unconditional. So we don't want to assume the generalized Riemann hypothesis. And so this is where things get really interesting. The L function could have one of these exceptional zeros. And it's a real, if it exists, it's real, it's simple, it's very close to 1. And therefore it makes it difficult to get a lower bound on L of 1 and hence on the class number. So wrapped up in all of this with the class number is these special values of L functions. All right, so we have 2 adjacent goals really. One of the goals you could say is I want an unconditional lower bound on h of k that's strong enough that I can do this classification. And on the other hand, a strong enough unconditional lower bound on the L function at 1 to eliminate the possibility of an exceptional zero. That would be amazing. And so the reason why these 2 problems are hard is, well, they're wrapped up with one another. So progress on one could lead to progress on the other. But as I'll point out, it kind of depends on the strength of the bounds. All right, so almost done with the history, and then we'll see what this connects to with gaps. So Siegel in 1935 proved a very strong lower bound on the class number, but the implied constant isn't computable. So in this classification that we have, this lower bound won't help. But then Goldfield and Grossagier proved a very strong enough lower bound on h of k where the implied constant is computable. And it's strong enough so that Watkins has computed complete lists of fundamental discriminants which yield class numbers all the way up to 100. All right, so it's strong enough here. But it's not strong enough to eliminate the possibility of Siegel zero or Landau-Siegel zero. And so now the question is, what does this have to do with gaps between zeros of the zeta function? So what I'm about to show you was already known by Montgomery. It was really the motivation of Montgomery's pair correlation conjecture. And also in a conference, I think in the 90s, Heath Brown gave a lecture that also talked about this connection to gaps. But it was actually first written down precisely by Connery and Advanians in 2002. So here's what their theorem says. This is a kind of a watered down version of their theorem, but it's got everything in it that we need. So they proved that if for all large t, they're greater than t log t to the 4/5, positive proportion, getting a positive proportion of zeros will definitely be enough for this theorem. So you can just look at this. If there are a whole bunch of zeros of the zeta function such that their difference normalized by the average spacing, it's a little bit smaller than a half, then the L function has this strong bound at 1, and the implied constant is computable. So what this theorem is saying is that if you could show that there are, say, more than infinitely many, like a positive proportion of non-trivial zeros, whose where mu, say, is less than a half, then you would get this very strong lower bound on the L function. Now, what does this give you? On the one hand, if you're interested in class numbers, it gives you a lower bound as strong as Siegel's result, but now with the implied constant. And it tells you that there are no exceptional zeros. It's a strong enough lower bound on the L function. Okay, that would be huge. So when you're saying like, what's going on with a half? Why are people working on this problem? Well, the idea is all kind of wrapped up in this theorem here that kind of shows how all of this is coming together. And I should just say that the way that this result comes about is really interesting. So basically, the idea is that if the L function does have an exceptional zero, so if it does have an exceptional zero, then this forces the zeros of, okay, so let's look at it this way. Let's say that you're in the quadratic extension. And you look at the Dedekind zeta function attached to this extension. Then the zeta function factors, or the Dedekind zeta function factors as the zeta function and the associated L function. Okay, so here's the way the argument goes. If there is an exceptional zero, then this forces a really bizarre behavior amongst the zeros of the Dedekind zeta function. It actually forces the zeros of the Dedekind zeta function, and hence of the Riemann zeta function, to line up in half integer spacing in clusters. It's called the alternative hypothesis. So the existence of this would force this weird behavior. So if you could prove that this behavior never happens, then you would show that there's no exceptional zero. And so it suffices to just look at the zeros of the zeta function because those are wrapped up in the zeros of the Dedekind zeta function. That's the idea of what's going on. Okay, so when we look back at this list, this small gaps progress, you know, here we see, now we have an idea of what's really driving these type of numerical results. And here, like, the half really seems stubborn. And you might say it's just because of the connection to the class number, but that's actually not completely clear if that's what's going on. So what I'd like to do is I'd like to tell you a little bit about this method to kind of show you its limitations. And I want to point out again that this assumes the Riemann hypothesis, and the results only hold for infinitely many zeros. So even if you were to beat the 1/2 barrier in this method, you don't win the big prize because you haven't shown that the result holds for enough zeros. But nonetheless, you know, we have to start somewhere, you know, and then see what we can adjust. So I want to show you kind of how this argument works to understand its limitations, and then talk about what if you don't assume the Riemann hypothesis, what can you get? Because all of these results assume the Riemann hypothesis. Okay, so before I kind of jump into that, maybe I'll take a sip of water and see if there are any questions. Okay, so this approach to small gaps was originally developed by Julia Mueller, who used it in the context of large gaps. She used a result of log𝛾𝑛. Later, it was determined just a couple of years later to also be applied to small gaps. And it's equivalent to a more complicated method due to Montgomery and log𝛾𝑛 from just a couple of years earlier. This is all going on around the same time in the early 80s. And so the idea of this method is that you're going to take usually polynomials and you're going to compare averages of this polynomial. Now, you're going to choose at the end what you want the coefficient to be. But suffice to say, we're going to look at two averages. One's a global average. So we'll look at how the polynomial behaves between t and 2t on average. And we'll also look at a local average. This is around zeros of the zeta function. And this average, this is located around some sort of size of a gap. All right, so I'm going to draw some pictures to make this a little helpful. I've got my little cheat sheet bubbles up at the top for all this notation. But the idea here is there are two very important observations that you have to make for this method to work. The first is that the local average around zeros of the zeta function is monotonically increasing. Now we can see this quite easily. Here, the summand is non-negative, and as we increase the length of integration, then we'll get something that's monotonically increasing. All right, so this is one very important observation. And the other important observation that I'm just going to gloss over, but if you're interested, I can tell you more about it at the end, is that if I evaluate the local average at mu, remember mu is the same mu from the beginning, it's a little bit less than 1, at least we know that. And if I evaluate the local average at lambda, remember lambda is some parameter that's greater than 1, then we get this chain of inequalities. Right, so I'm going to gloss over the details here. It's really just a measure theoretic argument. But this inequality here, this chain of inequalities is kind of the heart of the method. All right, so let me show you why. So I'm going to, all right, so here. So notice that if you believe this chain of inequalities, then if you can find a number c that forces the local average to be smaller than the global average, then because of this chain of inequalities and because M2 of C is monotonically increasing, lambda has to be greater than C. You get a lower bound on C. And on the other hand, if you can find a C for which the local average is greater than the global average, then the only way to fit this into the chain of inequalities would have to show you that mu is less than C. And so what it comes down to then is if I want a small gap result, I want M2 of C to be greater than M1. I want this ratio to be bigger than 1. And so I've got to find a polynomial and a value of C that makes that happen. And for large gaps, I want the ratio to be less than 1, meaning I need to find a polynomial and a number C that forces this to happen. All right, so here's because we've got a lot of notation, just to remind you. So here's the average. Average around zeros. We've yet to choose exactly what our polynomial is, and here's the global average. And this is the thing that I want to show is greater than 1 for small gaps. And so now we say, well, this local average is supported on zeros of the zeta function. And I want this ratio to be big. So I should choose my polynomial to be big around zeros of the zeta function. Okay. Well, 1 over zeta is big around zeros of the zeta function. Unfortunately, the Mobius function isn't so easy to work with. So instead, we'll take zeta of 2s over zeta of s, because now we have the Liouville function, so different lambda, completely multiplicative, so much easier to work with. And this informs a choice where we can say, well, let me just take a polynomial, a truncated version of this. All right, so here, this is just a little toy example. If you use this choice of polynomial and you work out all the mean values, so here's the hard working part. This one's not so bad. It works out to be kind of this nice expression right here. And earlier I said with these problems, you kind of hold your breath, right? So what you do is you work out the mean values with your choice of polynomial. And then you go to Mathematica and you say, what's the smallest number C I can find that forces this, again, it's the ratio, to be bigger than 1. That's what I'm trying to get to win. And in this little toy example, 0.5181 works, right? So that automatically gives me an upper bound on mu. All right, so now the question is, what other polynomials could you choose to get superior numerical results? So Turnage-Butterbaugh choose something very similar to the little toy example I just gave you, but they also multiply by the R divisor function. So this is a function that approximates 1 over zeta of s to the r. Definitely big around zeros of the zeta function, and it gives you another parameter to optimize over, which is really helpful. So here's where they win a bit more. And so then subsequent refinements in this process have been to say, now let me multiply by some smoothing function. And every single time you do this, it ends up being a polynomial of small degree. But that gives you the degree to optimize over, the coefficients to optimize over. And so this first approach of combining this was due to Bowie, Milinovich, and Ng. And then now you say, like, how much can I play around with this? But it's suffice to say, getting everything in a place where you can actually test it takes a lot of work. And so then you really are saying, man, I hope this pays off. All right. And I've been one of these people who you do a lot of work and then you're like, well, it produced a bound, but it's not the winner. So, oh, well. All right. So it's frustrating. However, I should be very clear. There are limitations of this method. So Turnage-Butterbaugh towards the end of the paper showed that they're not going to be able to beat a half for any choice of A of K. And Tim Trudgian has actually already worked out, it's worse than that. It actually can't even beat it can't even get to a half at all, right? It can't even beat 5, 0, a little bit more than a half. And so one thing that I've been thinking about is, well, what if instead of using these polynomials, maybe you use some generalized counting functions? So this method is in the context of the setup that I've just given you. In progress work with Goldston, we're showing that it also can't beat the 1/2 barrier. But this is the best method we have, right? So we're trying to figure out how much can we push it. Now you might say, well, in the polynomials that you're averaging, maybe if you could increase the length of the polynomial, you could get a better approximation and therefore win. So this has been explored by Connery, Vanderbilt, and Sound. They show assuming the generalized Riemann hypothesis and using their asymptotic large sieve, that you can get a lot smaller results for Dirichlet L functions. But they assume the generalized Riemann hypothesis, right? So that means that you're not going to say anything about non-existence of Landau-Siegel zeros because you're already assuming they don't exist. And also, Arian in his 2016 thesis had shown, well, what if you had a longer length of summation and you did this for the zeta function? Well, you can beat the 1/2 barrier with this method, but you assume lots of different things to get there. Okay, so there are ways to push the method, but then you're kind of giving up what you're willing to assume. Right. Okay, so now what I want to do is take another deep breath and start over again. All right, so if all that notation was kind of overwhelming, let's just start a similar question over again. All right, so it's a re-entry point. So what if instead of consecutive gaps, you were interested in R gaps? So maybe here's gamma of n and here's gamma of n plus r. We're going to do the same setup. I even just copy and pasted this slide and wrote little r's everywhere. All right, so here, this is now 1 on average. And so we're looking at lim-imps and lim-sups of this. When r is equal to 1, that's everything I was just talking about. All right, so when you ask yourself what's known in this more general problem, the answer is that, let me tell you a funny story of me trying to figure out what was known. All right, so in 1947, Selberg announced the following result in his article, The Zeta Function and the Riemann Hypothesis. All right, so he said, another result which shows the irregular distribution of the gammas is that there exists an absolute positive constant theta such that for all r, the lim-sup, so here this is gamma r, And here, this is mu r. So he's saying that the lim sup should always be bigger than 1, and we have an absolute constant. And the lim imp should always be less than 1, and there's an absolute constant that achieves this. Okay, so that's in his 47 article. But then if you have a good memory, I told you that Mueller was the first to give a result on large gaps between zeros. And in her paper, in the acknowledgement section, she says she thanks Gallagher and Montgomery and Selberg for communicating to me the following result. All right, so this is different. There exists an absolute positive constant C, such that for all positive integers R, the lim sup is not 1 plus C, but C over square root of R. So it actually depends on R. And the lim imp is not 1 minus the absolute constant, but 1 minus the absolute constant over the square root of R. And he notes that he was just missing this factor in the previous paper. Okay, so he was like, okay, that is, of course, and of course, these are statements of results, but no proof. Okay, so then, and here's where the story ends. If you have Selberg's collected works, the 89 publication, this is where everything is clarified. So here Selberg clarified the correct statement. And this is right here. And he says, as the manuscript of this paper was hastily prepared, there were inequalities misstated. We've all been there. Okay, so what I had proved was that these inequalities were true if one replaces theta with not theta of r to the like -1/2, but it depends if you assume the Riemann hypothesis or not. So he's saying if you assume the Riemann hypothesis, it's just like what was in Mueller's paper. But if you don't assume the Riemann hypothesis, you get a different power of r in the denominator. Let me rewrite this so it's a little clearer to say. So here is Selberg's results on R gaps. Under the Riemann hypothesis, there exists an absolute positive constant A, such that for all positive integers R, the small gap is less than 1 over A divided by root R, and the large gap is 1 plus A over root R. But unconditionally, the square root of R changes to R to the 2/3 in the denominator. All right, so this is the correct statement of the result. But one thing that I found very curious is that while I believe it, I mean, of course, I believe that Selberg did this, it would be nice to read a proof, right? It'd be nice to know what the result is. And it would be nice to have these results stated in a way that, depending on which paper you pick up, you really know the history and what you should be aiming for. So under the Riemann hypothesis, Connery and I in 2018 gave a proof to Selberg's statement for this is for the conditional statement. So, and we found constants. We went ahead and worked that out. They can be strengthened if R is bigger. But the idea is the method that I just detailed for you, the Connery-Log𝛾𝑛 method, this method depends on the Riemann hypothesis. So the explicit formula is floating around in there. That's kind of in the scaffolding of the method. So we adapted it to detect R gaps, and it all again comes down to averages of polynomials. And we made kind of like the obvious choice without any attempt to kind of strengthen these numbers. And after adapting the method, it all goes through quite nicely. All right, so this was like during my postdoc, we worked this out together. And I thought that it would be really nice to just once and for all give a proof to the unconditional statement. Just have it done, right? So what exactly are people looking for? This way somebody will say, this is the result, and here's a proof if you want to read it. But that gets a little harder. And so this is what I've been kind of working on. All right, so here is Selberg's unconditional result. So this is what I would like to give a proof of, because there's no proof in the literature. And there are two goals that emerge from working out what I want to prove. So the first is to give, the main thing is that I want a proof of the unconditional statement for R gaps, but we should start with R as 1. right? If you notice that in that big chart I gave you, there are no unconditional results stated. Everything depends on the Riemann hypothesis, which means every method depends on the Riemann hypothesis. So instead of trying to, figure this in one swoop, it's like, well, let me try it with R as 1. Let me see if I can give an unconditional result. And heck, while we're at it, maybe it could hold for a positive proportion of zeros, because that kind of problem, that kind of result is what we're really after in terms of the Siegel zero class number underlying pieces. Well, when I started this, I knew there is one proof in the literature that is unconditional for small gaps. Now, large gaps has unconditional proofs, but for small gaps, the only one is back in that chapter 9 of Titchmarsh, the sketch that Heath Brown gives. And so that seemed like a good place to start. So as if you recall, I told you Fuji and Selberg both observed that you get these strict inequalities, and that Heath Brown gives a proof of this when R is equal to 1. And what's so really cool about this proof is that it's unconditional and the results hold for a positive proportion of zeros. So for the R is equal to 1 case, the question is, can the argument be used to provide explicit results? And then can we adapt it to R gaps? Okay, so now that I'm going to tell you kind of the end of the story and how this goes together, let me ask Ian. Ian, am I finishing at 11:50 or 11:55? What is your target?
You officially have till noon if you'd like.
Oh, okay.
Yeah, take a little more time if you like.
Okay, great. Thank you. Okay. So the answer is yes, you can do this. First pass. All right. So Tim Trudgian and his student Alexander Simonič and I, in a preprint from last year, showed that unconditionally and for a positive proportion of zeros, we can explicitly say that lambda is greater than 1 and mu is less than 1. And okay, so we show that it can work. We got to work on these numbers a little bit. So here delta is very, 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 very small. All right, but nonetheless, it's a proof of concept, right? That we can get explicit results holding unconditionally for a positive proportion of zeros. And so you might wonder, well, can you work harder and do a whole bunch better? And then the answer is like, how hard do you want to work? And what do you consider substantially better, right? These are all subjective things. So we'll talk about this. But what I want to do is first kind of give you a peek into what we had to do to achieve this result. And then it kind of also shows what our next project, what we're working on right now, is like expanding this to R gaps. So Heath Brown, this is a little punt. So Heath Brown says, let me sketch the argument. So what I'm going to do is sketch Heath Brown's sketch. And what I want you to think about throughout this argument, this method, is that anywhere you see a less than, or a greater than, we make all of this explicit. And I'll point out the place where this becomes kind of the most interesting. So here's the method, completely different method on that Heath Brown sketches. All right, so we're going to have a set where we count ordinates of zeros whose consecutive spacings are large and are small. All right, and Heath Brown shows that there exists a lambda greater than 1 such that the set of ordinates for large gaps is greater than n of t. So that's your positive proportion. And that there exists a mu less than 1 for which the number of consecutive zeros that are closer together is also greater than n of t. And an interesting facet of this method is that you actually have to do the large gap calculation first. And how good you do in that calculation will force how well you can do on the small gaps. All right, so the input for how well you can get for mu, it depends on lambda, and not just lambda, whatever your implied constant is here, it also depends on the strength of that. So you've got a lot of places to work so that you can get the small gaps result. And this is just an interesting facet of the method. Okay, so let me show you kind of how this works. So what you do is you say, I want an interval between t and 2t that doesn't have any zeros. So that, let me say this precisely, n of t, the number of zeros up to t, is exactly the same as n of t plus 2 pi lambda over log t. So the way this looks in practice is you say, here's my interval from t to 2t, and I've got my zeros, and I just want to start my little window, and I want to say, like, when is it free of zeros? All right, so it's free of zeros here. So this is where the interval I would start. And it doesn't even have to be an interval. It could be a collection of intervals. So here it would end. And, you know, it could be the case that I starts back up again, kind of like here. And I guess it would end, you know, somewhere right here. So I is just a subset that's free of zeros. And you could think about it as it might be like one interval, or it might be a collection of little subintervals. All right, so if we're looking at the set, we want to count the zeros that are larger than average, then the measurement of this interval I is the bridge. Okay, on the one hand, you can say, well, the measurement of this interval is definitely less than the sum of these gaps between these large spacings. And on the other hand, it's more delicate to show that the measure of I is greater than t. This is where the kind of interesting things happen. Well, let's say you assume it for the moment. All right, let's just say that you agree that's true. All right, then we use Cauchy-Schwarz we square this piece here. We use Cauchy-Schwarz and have, this is counting how many of these pairs of zeros we have. And here is a calculation that we have to compute. Now, Fuji showed that this is less than n of t over log squared of t. And we got a little lucky here. This had already been made explicit in the literature unconditionally, so we were able to piggyback off of that. But if you believe this lower bound of t and you use this result of Fuji, then just dividing, you got this really is the number of zeros that are further apart than average is greater than n of t. But the cool part here is really showing that the measure of this interval is greater than t. All right, so how do we do that? That's kind of the input that we need. Well, remember that if t is in I, then the number of zeros between n of t and n of t plus 2 pi lambda over log t are the same. So for t and I, this difference is equal to 0. On the other hand, if t is not in I, this difference can fluctuate. And so we can make sense of this difference via the Riemann von Mangold function formula that I gave at the beginning at the top. So what we want to do is we want to study how this piece here varies as t is in t and 2t. Now, there are two things that we can do. So one thing we can do is we can say, well, let me just take this piece of the puzzle and do this moment calculation. And we can work out and show that we've got a term of size t. Here's the measurement of that interval we're interested in, and a lower order term. And so if we can show that this piece here is greater than t, then it has to follow that the measurement of I is greater than t. Now, how do we do this? Well, this is where we pop over to the argument of the Riemann zeta function. And now we have to start studying moments of the argument of the zeta function on the half plane. So it suffices to show that this moment here is greater than t, and we can do that with Holder's inequality if we get a lower bound on the second moment and an upper bound on the fourth moment. If we can show that each one of these is a size t, then by Holder's inequality, we get what we want. This is really our main task. So Fuji did this in the 70s, and so our main task was making this explicit. Okay, so once you do this, you're done, you get the large gap result. And so now I can tell you a little bit about the small gap setup. You start with this same sort of calculation here, this neighbor spacing. On the one hand, you can say, oh, it telescopes. It's equal to t plus a little bit, because gamma of n might not happen at t and 2t. So that's what's left over here. And on the other hand, you can work harder and get a lower bound for this summation that involves all sorts of good things. So here's the mu that you want. Here's the size of the set that you want. Here's lambda, that's your large gap result. Here is the size of how many large gaps you have. And let's let eta be the implied constant that we got from before. All right, so all of these things together tell me how good I can win on the size of the small gap pairs of zeros. And in this way, this is how you get what you want. So maybe just, I know this is a ton of information, but the idea is that the inequality that is interesting and your proportionality constant depends on all of these different parameters. All right, so the key insert in the proof really then comes down to this inequality. And again, as I said, you can do this through Holder's inequality by getting a lower bound on the second moment and an upper bound on the fourth moment. And we make these explicit. I can tell you first, what do I mean by explicit? So here are the constants that we got. Again, not working for the best one, just showing proof of concept. And the way that we do this is we approximate the zeta function, or the argument of the zeta function by means of a trigonometric polynomial. This depends on a certain zero density result kicking in at a certain moment. And this is one reason amongst many that it was nice to have Simonič on the project, is because these zero density results are directly related to his thesis. So it was really nice to have him on the project. All right, that's what it is, but anyway. Okay, so you might wonder at the end of the day, so we have two kind of remaining questions. Can we go back through and work even harder and get better explicit results? And then what do we have to do to extend this to R gaps? So in terms of the limitations of the method, it's quite murky. And the reason why it's murky is because there is like your constants chasing. There are all these constants coming from all different parts of the literature. And it's kind of hard to say exactly, just at this first pass, it's hard for me to say exactly what the limitations of the method are. But let me just show you that when you're figuring out the proportionality constant for the large gap result, there are some key constants that are popping in that we're able to estimate, but maybe we could do better. So for example, what is this K? All right, so this K comes from getting an upper bound on kind of this little second moment type of argument. Now, Korolev, so we didn't have to work this out because we just piggybacked off of a result of Korolev. He showed unconditionally, here's a huge value for K. Unconditionally or conditionally, Fuji has shown you can take K to be 9. But maybe it's even better. Maybe you could use like results from random matrix theory to tell you exactly what that K should be. So that's one place for improvement. There's also this M. Now I've used the same notation in the paper just in case you go back and want to compare. But this M comes from doing the second moment of the argument of the zeta function, these shifts. And we get this inequality and we have to show it's positive, and we can show it's positive if M is this number here. But if you've got a good eye, if your eyes haven't glazed over yet, you see, oh God, Caroline, there's another constant in there. It's a C. All right, this comes from some results of Karatsuba and Korolev. So if you want to improve that, then you have to go back to those papers. But once you have the M, this here, then you get this, it tells you what this other M1 is. This is just the constant from the lower bound of the first moment. So by taking these unconditional results, there are some results that are already in the literature, some that we had to work out for ourselves. This is how we arrive at the answer I gave you before. You know, but maybe you could do better. So maybe you say, well, what if I just said, let me take the conditional argument from Fuji. What if I'm so good at all of my calculations, I never have error terms? Okay, that would mean M is 1. All right, we know that's not going to happen, but let's say you were a superstar. That would force this other constant M1 to be quite small. And so with this kind of like very hypothetical wishful thinking setup, it seems that from this setup, you could get, okay, that's a lot further away from 1 than I first showed you. However, I should say that the large gap results, the record, right now is 3.18, and that's unconditional, right? So a different method gives you something better. And for small gaps, it seems from the setup you could get quite further away from 1 than what I was first describing, but still quite a ways to go to a half. All right, so what am I doing now? One thing I'd like to do is say, okay, if I just assume random matrix theory, what is this method really going to give me? All right, just to know that once and for all, because then you might say, okay, I'm done with this method, I'm going to do another one. Let me come up with another method. And then also going back and just settling once and for all this, I hate to say gap in the literature, that's a bad pun, but there's this gap in the literature. There's no proof for this unconditional Selberg result. And I'm really confused, like, where does this R to the 2/3 come from? I'm really interested in seeing kind of where that shows up. All right, thanks so much for your attention. I appreciate it.
All right, well, let's thank Caroline for a very beautiful talk. Any questions? Yeah, it is very hard to make even incremental progress in this field. It is amazing how much goes into it.
Yeah, it's really, I appreciate you saying that, Larry, because it takes, it's a hard problem for a reason, right? Like all these connections to the equals zeros and the class number shows you that it's a hard problem. And so really at the end of the day, you have to decide, what am I willing, how much work am I willing to do? The reason that I want to, there are a couple of reasons why I want to do this piece here. One reason is because I'd like to know, really, should I start working on developing a new method? If it's just not going to beat a half or even get close, kind of, to really understand the problem better. And also, I've just always wanted to learn more about how to make these conjectures with random matrix theory. So I know the L function recipe, I know how to do it for moments, but I think it would be cool to do it for all these other things. And so I'm like, sure, I get to learn things on the random matrix theory side. And also, just for the R gaps, like I hate it. I mean, I'm sure that you all understand there's so many results in our field where it's like, well, people know this. And it's like, well, not everybody knows it. Like if you're connected with the community, then you know, but if you're trying to get into the community, you don't know. And I just think it would be really nice to have just a proof once and for all.
Yeah, I totally agree with that. I mean, sometimes it happens that people will say, well, experts know this, but that can kind of hold back a field a little bit after a while. If people say experts know it, but there's no proof written down, and it's very beneficial. It's always very beneficial to the field when that stuff is written down, rather than it becoming a chain of things that experts know that is not written down anywhere is not ideal. Yeah.
Yeah, and I'm so happy, with this Connery and Ivanez, they wrote down precisely this result that experts had known about the connection between the vertical distribution. And, in Montgomery's paper, he says, I think he talks about beating a fourth, but then he said even beating a half would have major consequences. Yeah. And then he stops talking and you're like, wait, tell me more, tell me exactly what I need to do. So it's nice that that this is written down precisely.
Yeah. Great.
I have one quick question.
Yeah.
I think so. Maybe the obvious thing is how much of this work, or do you see any obvious roadblock to extending this to other Dedekind zeta functions or things like that?
Yeah, so the way I actually got started in this problem, my very first problem as a graduate student that Micah Milinovich, my advisor, suggested, is he said, so there's a whole different method, a whole different approach for large gaps. And the idea is you take your function and you study high moments. And as we know, high moments of L functions are also a big problem in analytic number theory. So I did this for Dedekind zeta functions of imaginary quadratic fields and learn the ropes, so to speak. But if you notice, if you've got a function, an imprimitive L function, So if the zeta function is lurking in there, then the small gap results is just going to come down to what you can say about the zeta function, right? So for large gaps, you can do this even if the L function is in primitive. And then I had a group of students at an REU a few years ago at Williams have them do GL2 L functions. Again, it was the large gaps argument with doing moments. And then, you know, these kids are like so sharp. I think halfway through the summer, they're like, we did it. And I was like, you're not done already. And they're like, no, we did it. So then I said, okay, so now I want you to do small gaps. And I think I had them do primitive functions. And in hindsight, you know, I should have probably asked them to do it for automorphic L functions. And I said, just do the Selberg class. So you can do it right there. And I think they use the pair correlation approach for these other primitive L functions. But as soon as you get something that's in primitive and you're talking about small gaps, and actually the Connery and Avanians paper looks at zeros of Hecke L functions. So the version that I stated for you was kind of the nicer one where you're saying, okay, let me take a Dedekind zeta function. So this can be explored, but kind of at the roadblocks, it's either for large gaps, it's high moments. We aren't good at doing those. And for small gaps, it comes down to the zeros of the zeta function. Yeah.
Thanks.
Yeah.
Okay, well, if there's no further questions, let's thank the speaker again.
Thank you.
Action button. All right, well, thanks so much.